I said last time that if you're using a heuristic function with A star, and that heuristic function is guaranteed to never overestimate the cost to the goal, then you're guaranteed to find the minimum length path. So it turns out that that's not quite true. That's true with A star if you're not using multiple path pruning. But if you're using multiple path pruning, there's a slightly stronger restriction on the heuristic functions that are going to work. So let's take a look at that. This is described under the multiple path pruning section here. And here he lays out something bad that can happen even with an admissible heuristic function. And this is the stronger restriction, this monotone restriction or the consistency restriction that we need to satisfy in order to use multiple path pruning with A star. And it's that the difference of the heuristic function between n prime and n is less than or equal to the actual distance between those two nodes, n prime and n. It seems a little mysterious. So what I want to do is sketch out an example that sort of illustrates what he's concerned about here. So here's a graph that I want to look at. Here's my n prime, here's my n, and the goal, we'll call this the goal. Notice that the shortest cost path, the lowest cost path, is this one, and it has a path length of 7. There's an alternate path to goal, which is this one, which has a path cost of 9. So obviously, in order for our algorithm to be correct, it needs to find that length 7 path cost. So let's imagine a heuristic function here, and I'm going to come up with a heuristic function that violates this constraint. So here's my heuristic function. Here's the estimated minimum cost to goal from n prime, and I'm going to make that, we'll say 6, and my estimated minimum cost to goal from n will be 0. So let's check these for admissibility to make sure that they don't overestimate the cost. So this is fine, right? It clearly isn't an overestimate estimate. It estimates that the cost will be 0, and it's actually going to be at least 5. And this is not an overestimate, right? The estimate is 6. There's a route to goal from here that requires a cost of 8, and there's also a route that requires a cost of 6. So this is not overestimating the true cost. But it does violate our monotone restriction, right? The difference between these two is 6, but the actual distance between them is only 1. So why is that a problem? Well, let's just start running A star with multiple path pruning and see what happens. So this is added to the frontier, and the f value for this node is going to be 3, right? It's the cost of reaching that point in the graph plus the estimated cost of getting to the goal. Similarly, the value for this guy is going to be 7, right? The cost of getting to that point plus the estimated cost of getting to the goal. So something terrible happens next, right? A star is going to choose the 3 and expand that 3, find its way to the goal, and return this path as the minimum cost path. And recall that once a node is removed from the frontier in A star, that's it. There's never another chance, right? It's added to the explored set if you're doing multiple path pruning, and there's never going to be another chance to find a different path through that node. What went wrong? So these two heuristic values make some sense when considered individually. Neither overestimates. But when you look at them together, they tell this inconsistent story. Right? From this point, we somehow believe that it's going to take us at least a cost of 6 to get to the goal. But then whoop, we take one step here, and all of a sudden that estimate drops, and we think it's going to take us this 1 plus 0 additional, so 1 step to get to the goal. So why wasn't this heuristic value 1 to start with? That would be consistent, right? That way these two are telling us a story that makes sense together. And in fact, I won't do it, but I'll let you, if you'd like, take a second to rerun our A star algorithm with this newly consistentified heuristic. or any pair of values for these heuristic values that are admissible and that are within only one of each other, you'll find out that everything works fine. Keep in mind that this admissibility requirement is only in place, this consistency requirement is only in place if we're doing multiple path pruning. Why is that? Well, if we're not doing multiple path pruning, it doesn't really matter that this guy ends up explored first, that this path ends up explored first, because we'll have a chance to explore that other route through that node. We won't throw out that route once we get to it. And because of the admissibility constraint, we'll still have the guarantee that by the time we actually pull the goal node off the frontier, we'll have truly found the minimum cost path to the goal. So this seems a little bit ugly. The good news is that there tends to be a pretty small gap between admissible heuristics and consistent heuristics or monotone heuristics. You have to go out of your way a little bit to develop a heuristic that's admissible but that isn't consistent or monotone. Most natural heuristics that you come up with, like our straight line distance heuristic that we use for the robot, are both admissible and consistent.